Hello there, welcome. This is a drive-by code session. It's been a while since I've done one of these, so I might be a little rusty. I'm going to continue our video series about how to make a computer programming language. So we're getting towards the sort of later part of how to use Nearley.js to build out a parser. First, before I start, I want to tell the viewers, all of the two or three of you, about a project that I have started. It is called the Fun Programming Language, or the Fun Prog Lang, if you will. The Fun Programming Language is a very small programming language. It's a proof of concept programming language. The purpose of it is to teach developers functional programming. It allows you to use a pure functional syntax using the fun keyword, or a imperative style programming using the proc keyword. But the secondary, or perhaps the primary purpose of building out this language is to have, for people like yourself who are trying to learn how to implement a programming language yourself, this is a project where you can have a working example, which you can dig into the source code, tweak it, muck with it, break it, and use it as a learning tool. So if you're interested in checking this out, that's the URL. It's github.com/airportyh/fun-lang. And also, I've been getting some amount of comments on these videos, and that's quite assuring to know that there are some of you that are actually watching these videos. I want to read one of these comments and address the question that this viewer had. The viewer's name is Nasty Mixture, and he made this comment 1 week ago. On the video about handling white space. Okay, on the video about handling white space, he asked, how do you handle newlines in your grammar? Evidently, in my example, I didn't handle newlines. I do believe in JSON handles newlines, and the fact that I didn't is a glaring omission. So my answer to him is that you can just put in newline string literals in your rules. That's one way. I'm gonna demonstrate it a little bit in my in the math arithmetic parser that we're working on. So this is the math arithmetic parser, which is at this point is able to add, subtract, multiply, and divide. But it can also do these simple functions like power, and it's got a number of built-in functions, including square, square root, sine, cosine, absolute value, and power. So you can call these functions. We were doing some powers of 2s here. It can also do addition, subtraction, and even parentheses, I believe. At this point, it can do that. So let me try. Oh, this is the replay terminal. Let me try running this parse script. And okay, I think that worked. I think the power of 2 to the 12 is 2 less than this number, so that seems to work. Let me change it to 2 to the 4th. Okay, yeah, that would have been 16 plus 2. So that seems to work. Question now is, how do we add the ability to have newline characters inside this string? So let's do that. Okay, so I have a string now. It's got some new lines in it, and I may even jam some new lines in the middle of this expression here, like that, because I want to format it nicer or whatever. And if we try to parse it right now, we're gonna get an error because the grammar at present doesn't handle new lines. I do have an existing place where I handle this optional white space. It's made optional because of this star operator. This means 0 or more occurrences of whatever that is. And the whatever that is, that's a character class that includes the space character and the tab character. So if I wanted to add new lines to the mix, all I have to do is really add the new line character into that character set, and it should be good. So now I want to regenerate the parser using npm run gen parser. And if you are very unfamiliar with all of the stuff we've done, you should definitely go back and watch the previous videos in the series. So gen parser takes this math.ne file and generates a JavaScript version of that guy, and then our parse script is able to use this generated JavaScript version of that guy to make a parser. So now if we run parse again, so that didn't work. I have a suspicion it's might be because of the beginning white space and the ending white space. I probably don't have a rule that says the input can allow for beginning white space and ending white space. So let me test that theory by removing the beginning and ending white space from it. And then indeed that worked. Now if I did want to allow for beginning and ending white space, then what I want to do is say the beginning input can optionally have beginning and ending white space. However, I need to fix this transformer function now, because if I left it as is and let it use the ID function, it would actually pick the first match symbol, which is a white space, and pass it on to the next part, which is not gonna work out. So I actually need to write a transformer function that takes the data, which is the array that contains these three things. So you can imagine this as an array that has white space, an additive, and then another white space. So the thing I want is at index 1. So I want to return the thing at index 1, I think. Regenerate the parser again, run the script, and now it works. Let me put the beginning and trailing white space to see that. Yeah, it works even with the beginning and trailing white space now. Okay, so that's how you can handle white space. And you could also optionally, if you wanted to match literally a instead of using a character class, you could use a string literal like that as well in your rules. Okay, so that's what I have to say about matching new line characters. Let's get back into what we're doing. So in this episode, the plan is we're gonna try to, whereas currently the code evaluates the result as part of the parsing process. So what I mean by that is if you have an expression like 1 plus 1, the parser, you as a string, you send that through the parser, and the parser, it is gonna give you the result, number 2. Okay, we're gonna change this process so that the parser, instead of generating the end result for us, it's gonna generate us a tree, which sort of looks like this. And we're gonna call this guy the AST, which stands for an abstract syntax tree, which I have sort of mentioned briefly in one of the first videos in this series. And the abstract syntax tree is very important for programming languages because it's a representation which computer programs can use to basically reason about the program or do concrete things with the program. The AST is basically a representation of what the program is when you wrote it. So this tree is a representation of this program 1 + 1, for example. And the reason we might want to do this instead of just calculating the result outright is because we may want to translate this 1 + 1 into another programming language, perhaps JavaScript, but perhaps lower level assembly language that the CPU is able to execute directly, or perhaps we might have other uses for the AST tree. One use for it, so I'm gonna write like other uses for AST, right? Why would you not want to just calculate the value outright and instead generate this tree representation of your program? Well, you might want to write a checker, like a type checker, but you might have things to check other things. So like a linter is actually a good example. A linter checks that your code is conforming to certain rules that the linter deems important. So those are a couple of other uses for AST. So that's the goal. We're gonna, instead of having the arithmetic parser generate the answer right away, we're gonna have it return an AST. So what does that mean from the grammar perspective? Well, a grammar perspective, let's say if we have, again, the string 1 + 1, currently the way the way the parser resolves this string is, well, the parser has to start at input, the input symbol, and then it's gonna go downwards in the tree and resolve it as an additive. And then in this case, we're gonna have it's gonna break it up into the left hand side and the right hand side with this matched plus sign in the middle. So additive is gonna have a plus sign and a multiplicative. I'll shorthand this, and another additive. Oh, my handwriting is really hurting this show, I think. And then the next additive can get resolved into the singular multiplicative. And then let me spell this out. Okay, and then this multiplicative is gonna get resolved over here. Oh, not over here, because this one would be a singular. All right, so it would actually get resolved as this unary here. This unary. Oh, this is getting messy now. So we're gonna get an unary. I'll just write unary for short instead of unary expression. Unary. And then an unary, it is gonna end up resolving to a number here. So is this one. And then number to a digit, and I think number has to resolve to digit and digits. I'm actually gonna skip a few steps then, because I'm running out of space. But the number resolves to digit, and digits to digit, and eventually we have the ones in the tree. So this is sort of the parse tree, and we don't want our AST tree to resemble this because that's too complicated. So what really happens in the parser when it's doing its thing is at the end, when a number is resolved, we have this transformer that transforms the string data that the parser has collected into a JavaScript number here. We put this decimal point in the case that there is one, but if there isn't one, it's just with the string of digits here, we put it together, send it to the number function to generate a JavaScript number for us, which in return sort of attaches this number to this number symbol in this parse tree. So we're gonna attach the number 1 here, and we're gonna attach the number 1 here. And then if we go up to the unarray expression here, oh gosh, let me try to remove some of these things. Okay, so an unarray expression, what is the thing that's gonna get attached to this unarray expression? That is gonna also depend on this transform function, what it does. In this case, if the unarray expression was resolved from a number, it's just gonna take the ID, which is whatever the value was from the level below. So again, the number 1 is gonna get attached, and that's gonna happen again and again, like that. So the value that gets attached to each symbol in these levels is gonna sort of propagate until the place where it combines. So this additive that has both a left-hand side and a right-hand side and a plus sign, that one is gonna happen here. So this rule is actually gonna combine this one with this one by adding them together here, and because it will use the case that this operator here is a plus sign. So the thing that end up getting attached to this additive is actually 2, and then this 2 will propagate, whoops, not 1, but 2. This 2 will propagate up to the top level input, and that's how the result of the parse is 2. What we want to do is, instead of attaching these numbers to these sort of symbols as we go, we actually want these guys to be ASTs now, instead of the actual values. And so how do we do that? Well, let's show it to you in code. Okay, so again, I'm gonna be replaying what Waikit has done. So let's see what he does. So the first thing he does is gonna start modifying this transform function for the additive in the case where there's both a left-hand side and a right-hand side. It's basically going to return an object instead of returning a numerical value here. And this object is gonna have a type. He's gonna call it operation. The up is the operator, which is coming from here, which is index 2, which this is 0, this is 1, this is 2. So index 2 is the operator. There's a left-hand side, which comes from this guy, and a right-hand side comes from this guy. So, and then he's gonna remove the previous one. So let's see what we are ending up with here. So basically, we end up with JavaScript object as the AST node. So this additive AST node is going to look something like this. Type operation, and then there's going to be an up, which is a plus sign, and then there's a left-hand side, which I actually don't know what that looks like yet. So I'm gonna write blank here and a right-hand side. But the left-hand side and right-hand side, what those are gonna be is gonna be determined by what is the return value, the value attached to the multiplicative like one layer down the parse tree, and the additive value one layer down the parse tree. And it could actually be yet another operation that's on the left hand side, because there could be another add or subtract or multiply operation, but it could also be a function call on the left hand side as well. So we don't know. So let's keep going. He's going to do the same thing with this multiplicative and return an object of the same shape here. And then removing the code that was returning a numeric value. And now we need to look at this function symbol. So this function rule handles built-in function calls. And currently we're doing these calculation here to actually calculate the square root and the square and the sine and cosine, etc. Now instead of that, we're not gonna do this actual calculation, and we're gonna replace it with an AST node, again, a normal JavaScript object that has a description of what this function call operation means. So we're going to say it's the type of this node is going to be function call. It's going to have a function name, which comes from the 0th element of these matches. That's the built-in function. It's going to have the argument, which comes from over here. That's index 3. You can count that. And then that's it. Now we're going to move on to number. So how are we going to actually represent numbers? We're also going to make that an AST node. We're going to just say it's a type number, but the value will be the actual number. And we'll do it once for the decimal number case and do it once for the integer number case. Regenerate the parser. He messed it up. It should be npm run. Oops. Don't type in here, Toby. All right, npm run gen parser. So he has regenerated the parser. Now he's gonna run this this parse script. Oh, he made a syntax error. I think we have to backtrack to where he made that error. It was here. He was missing a closing parenthesis over here. So fix that. Regenerate the parser, and now the parse generates an AST tree. So you can see this, the representation of this calculation, this power, or take 2 to the 12th power is maybe how we would call it, or maybe we are going to call the POW function with arguments 2 and 12. So therefore, the representation of this code is described in this AST. And the top level node is a function call whose function name is POW. And its arguments, there are 2 arguments. An argument is an array. The first argument is a number, which is 2, and the second argument is a number whose value is 12. Let me try something now off script. So if we did say 1 plus 1, our previous example, parsed it, then we get a AST, which is at the top level is an operation whose operator is plus, and the left hand side is a number, which is 1. The right hand side is a number, which is 1. So that's an AST. Okay, I'm gonna go back and follow Waikit's script now. So he's gonna try a couple of different things too. So we're gonna have, looks like the power, he's gonna do this power thing plus the result of a multiplication, and then the whole thing divided by 4. And you can see this AST can nest arbitrarily deep, because the calculations you want to do can become arbitrarily complex. And really that's a sign that whenever you want to represent, describe, or calculate something arbitrarily complex, that's a sign that you need a language. You need perhaps a programming language. So this tree now is an operation. It's a divide operation. So really, it's like this guy. The top level tree is really this one. This is an operation, right? It's a divide operation, and then the left-hand side of the divide operation is that guy, which is, what is that? That's actually a plus operation. I'm gonna simplify this. So this is left-hand side, this is right-hand side. The right-hand side of the divide operation is just a number of 4, but the left-hand side is this complicated thing, which there's so deep that the terminal doesn't even want to display it to you. And there's actually a trick. I think Waikit shows it off. There's a trick in Node.js to use something from the util built-in library. It's util.inspect, and it will give you the option of allowing more depth in the printout here. Okay, so let's see that. So now you can see all of the tree because we are allowing for depth 10. So yeah, so basically, so the left-hand side of this divide operation is this whole big old thing. And then what is that? Well, that is a plus operation, and it has a left-hand side and a right-hand side, and its left-hand side is a function call. It's 2 to the power of 8. See? 2 to the power of 8. And the right-hand side of this thing is a multiplication. It's a multiplication operation. It multiplies 2 to 3. So that's 2 to 3. All right, I'm making a mess now, so I'm gonna stop. So things are working, and this is a good state of things in terms of the code. Let's do one more thing. So we're gonna make it more convenient for the next step in our process, which is to save the AST into a file, and so that it's easier to read, and perhaps it's formatted nicer as well. And I like to use a library called MZ. That it really should be MZ. I think the recorder missed the M for some weird reason. We're using MZ. I really like using MZ, and Waikit does too. So for doing I/O with Node.js, like reading from the file system, etc. If you would like to learn more about MZ and using it with async await, I have made a video series on using async await as well, which covers that. Okay, so now we're gonna require MZ. This should be MZFS, I believe. But in order to use, I think he made a mistake here, but that's okay. He's gonna have to fix it later. But the way you use it with async await, the reason we like to use this is because we can use it easily with async await. So when we want to read a file, for example, we just await the result of the or if we want to write a file, I should say, in this case, we just await the result of the file write. And then we can write code in a straight line manner instead of having to use callbacks. So this is yelling at Waikit that he's importing an unknown module name, so it really should be mz/fs for mz's promiseified version of the file system module. Okay, so now we have written the ast.json. Let's go look at it. Where is AST? That's AST.json. Yeah, so that's what it looks like, and we went over the contents of this, but we have a file now with which you can go back and look at it. So that's really cool. I'm gonna stop this video here. Thank you for watching. If you have watched this far, please leave me a comment in the YouTubes, and I hope to see you next time.